Good morning, good afternoon, and good evening, everyone, wherever you might be. So today we're going to be talking a little bit more about scientific computing, and specifically, we're going to be going over this concept of linear systems. And so, okay, I'm just gonna write that out. But basically, well, linear systems um, is basically the solution of linear systems, right? It's one of the most basic aspects of computational science. And in many of these applications, the solution technique often gives rise to a system of linear equations, which need to be solved as efficiently as possible. So what do I mean by that? Well, when we think of linear systems, let's actually try to dissect what this means. When we think of the word linear, what do we mean by that? Well, we mean a line, right? And when we say a system, well, we can say, okay, well, we have y equals 3x plus 1. That's a line equation. And we have another line equation, I don't know, y equals 5x. This is a linear system, right? It has two linear equations in a system. So that's bottom line. That's the idea, right? So from a pre-calculus, it's a pre-calculus concept, the concept of linear equations. And if you have tons of linear equations and you want to solve for, if we go back to our previous example, you want to solve for an x and a y, well, that's a system. So here we solve for x and y, the values of x and y that satisfy both these things. And there are many ways we can do that. So yeah. Okay. So when we're doing linear systems, we want to solve it as fast as we can, right? So this is related to a previous video about computational complexity. We want it to be as fast as possible. So in addition to Gaussian elimination, there are a host of other techniques which can be used to solve a given problem. And so, well, this chapter of linear systems offers an overview of these methods and techniques. And ultimately, the goal is to solve large linear systems of equations as quickly as possible. Thus, the consideration of operation count is critical, right? The idea is we want to solve these linear equations as fast as possible. So we want to solve for x and y as quickly as we can, right? And one way, yeah, we know how to do Gaussian elimination, right? From a high school course, we can say, oh, let's subtract these two equations, right? And we can get 0 equals negative 2x plus 1. Okay, we can't solve it that way because I just made this up. How do we solve this? Well, we can plug in y, which is 5x. We can plug it here. And we now have 5x equals 3x plus 1. And then we can isolate. I mean, yeah, here we just solve for x. We get 2x equals 1. And then we get x is 1/2, right? And from there, we just plug it in here. And so here our y is, well, 3/2 plus 1. So that's 5/2. Yeah, and then if we plug it here, we also get 5/2 for our y. So yeah, those are the basics. But what if we have like tons of them, right? We have tons of equations. Well, that's a different strategy. So here we're going to talk about one of the strategies, which is the direct solution methods. So here we're solving for, again, linear systems, right? So for ax equals b. So that's the first thing we're going to be talking about. One method to solve this is just the direct method, the direct solution methods. for AX equals B. So a central concern in almost any computational strategy is a fast and efficient computational method for achieving a solution of a large system of equations AX equals B. Yeah, so this is a very, very large system, right? In our basic example, we only have two equations, but here we have a large amount of equations. So how do we solve all of those? So in trying to render a computation tractable, it is crucial to minimize the operations it takes in solving such a system. So basically, we want to make it faster. And there are a variety of direct methods. So here we're going to talk about the different methods for solving AX equals B. And well, here we have Gaussian elimination. So we're going to talk about that. We also have, what is this? LU decomposition. So we're also going to talk about that. And we also have inverting matrix A. So here we assume that A is a matrix. So something about inverting matrix A. Right. And in addition to these direct methods, iterative schemes can also provide efficient solution techniques. So we're also going to be talking about iterative methods. And so some basic iterative schemes will be discussed in what follows. The standard beginning, the discussions of solution techniques for AX equals B involves Gaussian elimination. So here let's do an example, right, of Gaussian elimination. So we'll consider a very simple example of a 3x3 system in order to understand the operation count and numerical procedure involved in this technique. Okay, so let's do that. So here we consider 3 equations and 3 unknowns, right? So here's our example. Just to start off, x1, x2, x3 is equal to 1. x1 plus 2x2 plus 4x3 equals -1. And then x1 plus 3x2, 3x sub 2 plus 9x sub 3. So here we have 3 unknowns, which are x1, x2, x3. And so we need 3 equations in order to solve all of them. In the previous one, where we only had x equals 3y plus 1, x equals 5x. Oh no, not x. Y x. Y equals 3x plus 1 and y equals 5x. Here we have 2 unknowns. So the pattern actually is based on the number of unknown variables that we need to solve for, that's also the amount of equations that we need. So if we have 1 unknown, we need 1 equation. We have 2 unknowns, we need 2 equations. So here we have, in this case, 3. Well, we need 3. Okay, and here we can rewrite this in matrix algebra. So in matrix algebra, we can rewrite this system, this linear system, specifically in the form AX equals B, right? So here, let me actually dissect what this is. A is a matrix. So A is some matrix with, let's say, n by m dimensions. Here V, or no, not V, X is a vector. So yeah, x is a vector with, so if we were to apply this, what's it gonna be? M by 1. And then b, as a result, is a vector. So if you guys don't know what these are, well, I have a previous video in my scientific computing playlist that talks about these. And so here b is a vector, n by 1, right? So these are vectors. So if we were to write this here, well, our matrix is 3 by 3 in this case. Our vector is 3 by 1. And so our b vector is 3 by 1. So let's rewrite it. So A is this matrix 1, 1, 1, 1, 2, 4, 1, 3, 9. Where did I get these numbers? Here. 1, 1, 1, 1, 2, 4, 1, 3, 9. That's where I got those numbers from. Then our x is a vector which has x, y, z. And our b has 1, -1. Okay, the textbook wrote it this way. Actually, I'm going to rewrite it this way. x1, x2, x3. Right? Just to follow the unknowns. So if we multiply ax, this would give us a vector b. So this is a matvec, right? A matrix vector multiplication, where we get the dot product. So we multiply this to here, which is equal to this. Then we multiply this to here, which is equal to this. Then we multiply this to here, which is equal to this. So we can just rewrite this like this. But here we just rewrote it in matrices and vectors. Okay. So the Gaussian elimination procedure begins with the construction of the augmented matrix. So what do I mean by that? Well, okay. So I'm just gonna write this out. AB, which is equal to here. And then we have 1, 1, 1, 1, 2, 4, 1, 3, 9. And then RB, so 1, -1, and 1. Now, okay. Let me double check. Okay, so in this first process, well, I actually underlined this one here. So let me just, actually I'll put it in red maybe. So this one here gets underlined. And what happens after is some number changes here, which is weird. Okay. Bolded the 5, the pivot. Oh, so we did some Gaussian elimination here. So what happened? What happened here? Yeah, because I'm trying to see a pattern. Wait, actually, I'll just show a screenshot. Yeah. So the Gaussian elimination that happened, I'll just show it. So here's what happened. Okay, let me make it bigger. So after writing it in matrix form, matrix and vector forms. So this is my A, my matrix A. Okay. And then this is my vector B. And in the book, it highlighted this one. And then you can see in the next step, here nothing changed in my first row. In my second row, everything changed, as well as in my third row. So what happened here? Trying to see. Uh, Maybe I subtracted something. This changed to a 0. This changed to a 1, to a 3, to a -2. Okay, let me Google how Gaussian elimination works. Okay, so it's a method for solving systems of linear equations by transforming the augmented matrix. Yeah, how does that work? It's either I could swap two rows, could multiply a row, or I could add a multiple of one row to another row. Okay. Right, let me see again. So okay, here are the three operations that I can do. It's either I multiply any row by a constant other than 0. I could switch any two rows, and then I could add two rows together, right? So here in this next step, what did I do? Did I swap anything? I don't think I swapped. Maybe I did, I don't know. Did I multiply? Uh, okay, I don't think so. Did I add two rows together? 1 minus 1, 2 minus 1. Oh, look at that. So my second row here, right? So let me just label the steps that happened actually. So subtract the first row from the second row. That's what happened here. So I subtracted 1 minus 1, and I get a 0. I subtracted 2 and 1, I get 1. I subtracted 4 and 1, I get 3. Subtracted -1 minus 1, -2. And these are switched here in the second row, right? So that's what happened. Okay. And then from here, so now I have this new matrix A and vector B. Now what did I do? Now, okay, now my 1 is here. I have this highlighted. So here nothing changed, right? Nothing changed in my second row. Nothing changed in my first row, but oh, look at that. Something changed in my third row. So what does that mean? Well, uh, let me see what happened here, maybe. Hmm. Did I do something with, not sure what I did. Oh, look at that. I can multiply any row by a constant. So what I did here is multiply my third row by a constant 1/2, right? So I divided this by 2, I get 0. Divide this by 2, I get 1. There's a 1. Divide this by 2, I get 4. Divide this by 2, I still get 0. So I multiplied it by a constant 1/2. Okay, now what did I do in my third one? So from here, well, nothing changed in my first row. Nothing changed in my second row. But something changed in my third row. I subtracted. So subtract first row from second row. So second row minus first row. So here I subtracted my basically it's these numbers minus these numbers. So I subtracted my second row from first row, right? Yeah, because I did, okay, 0 minus 0 minus 0, I get 0. 1 minus 1, 1, yeah, 1 minus 1, I get 0. 4 minus 3, I get 1. 0. Oh, wait a minute. 0 minus 2, I get 2. Oh, 0 minus negative 2. Yeah, 0. Yeah, I'm right. 0 minus negative 2 is just 0 plus 2, which is just positive 2. So that's why I did there. Now, you might be asking, why in the world did I do that? Because if we're doing a Gaussian elimination, well, here you notice we have all zeros here. There's a diagonal. So maybe there's some meaning to that we'll later see. But here you notice there's 3 zeros there in that diagonal. So, okay, let me just do, so this is basically Gaussian elimination. So for Gaussian elimination, the 3 things you can do: multiply any row by constant. So this is just mainly notes for me. By constant, except 0. Another thing you can do is switch any 2 rows. Yeah, I didn't take this in high school, so I just knew about it like right now. And then you can add 2 rows together. Those are the 3 things you can do with Gaussian elimination. And here are the steps that happen. It's just notes for me as well. Okay, cool. Now, now that we have this resulting matrix and vector, right? Because this is our A and this is our B. Well, this is apparently what we call an augmented matrix, if I'm not mistaken. Okay, there's some linear algebra stuff here that I'm still not sure of. So I'm just gonna trust that this works. But yeah, that's what happened. Now we have that matrix. And here we want to do back substituting. So I'm gonna talk about that. It's actually it's really simple. Back substituting gives this solution. So what do I mean by back substituting? Well, from this matrix and vector, right? Well, now we have, so here, right? Our A is now 1, 1, 1, 0, 1, 3, 0, 0, 1. Our x vector is now, well, our x vector is still the same, x1, x2, x3. And our b vector, as a result, has also changed, 1, -2, and 2. And so the back substitution that I was saying is, well, we back substitute. Okay, I'm kidding. We back substitute, right? So we start from here, the bottom of our matrix and the bottom of our vector. Okay, well, here we can see that, okay, well, I multiply this by this, that's a 0. This by this, that's a 0. And then this by this. And then I get the corresponding b value, which is this. So here we say, oh, x3 is equal to 2, right? And the textbook made it look this way. This is just the initial thing we got. So here we're starting from the lower part of the matrix and the lower part of the vector. Okay, so yeah, from here we got, yeah. And then, so the next thing we do is we move up, right? So we move up, we go here, then here. So here we have 0, x1, x1 times x2 plus 3 times x3. So we actually have x2 plus 3x3, which is just equal to, well, my second one here. So boom, boom, boom. So I have a -2, right? Okay, let me just move this here maybe, just so that's easier to look at. And what happens with that? Well, knowing that our x3 is 2, we can plug in x3 here for 2. And so we get x2 plus 6 equals -2. And here we say, oh, now my x2 has a number. It has -8. And lastly, I go to my first one here. So boom, boom, boom. And I actually get just the same thing as my previous system, which is x1 plus x2 plus x3 is equal to 1. And here I get my value for x1, which is just 7. I plug in my x3, so this is a 2, this is a -8, and so my x1 is 7. 7 minus 6 is 1. Yeah, so those are there. Great, I was able to solve my 3 constants, right? Nice. So this procedure can be carried out for any matrix A, which is non-singular. I don't know what that means, but cool. So in this algorithm, we simply need to avoid these singular matrices and occasionally shift the rows to avoid a 0 to pi 1 pivot. Provided we do this, it will always yield a unique answer. Okay. Det A, what does that mean? I think it means determinant or something. Det A. Oh, determinant. Yeah. So this, yeah, the procedure of Gaussian elimination can be carried out for any matrix A, which is non-singular. So what is a singular matrix? What's that? Oh, a singular matrix is a square matrix that does not have an inverse. Meaning there is no other matrix that when multiplied by the singular matrix results in the identity matrix. Oh, huh. Okay, I'm not gonna dive deep into that because I haven't had linear algebra before. Um, cool. Okay, but yeah, okay. So let's just go for the general facts here. In scientific computing, the fact that this algorithm works, so our Gaussian elimination algorithm, is secondary to the concern of the time required in generating a solution. So the operation for the Gaussian elimination can easily be estimated from the algorithmic procedure for an n by n matrix. So we move down the n pivots, and then for each pivot, we perform n additions or subtractions across the columns. And for each pivot, perform the addition or subtraction down the n rows. So here we talked about operation counts before. Um, so I'm going to state it. So the operation count, so here we'll use flops. So here we're saying the operation count for Gaussian elimination. Well, what is it? So yeah, we were given an n by n matrix. So here, one, we did movement down n pivots or n pivots, right? Okay, where did we learn about pivots? I am okay, cool. Okay, and then for each pivot, oh, for I think what it means when we say pivot is the number of changes that we did. Okay, let's see what that means. So we did movement down n pivots, and then for each pivot, so for each pivot, well, we do n, we performed n additions or subtractions. Okay, pretty cool stuff. Across the columns. So how did I see that? Well, we can actually count it. Let's see how many additions did we do across all columns. Well, okay, here we did, um, well, this is, okay, let's do a regular matrix vector multiplication. So we do a dot product of this and this. So that's going to be what? 1 times x1 plus 1 times x2 plus 1 times x3. And that will give us a 1. So it will give us this one. So how many multiplications did we do here? Well, we did 1, 2, 3. How many additions did we do? We did 1, 2, right? Uh, is this what it was asking for? I don't think so. Oh no, in Gaussian elimination, my bad. Sorry. It's not, no, it's not this. This is a matrix multiplication. It was asking for the Gaussian elimination. Well, yeah, every time we do so let's say here we subtract the first row from the second row. So the second minus the first, 1 minus 1, 0. 2 minus 1, 1. 4 minus 1, 3. Negative 1 minus 1, then that's... So here, how many additions or subtractions did we do? We did 3. 1, 2, 3. That's the idea, right? Our matrix, right? For, let's do this. N by N matrix. Yeah, so we did N additions or subtractions across columns. And also, so for each pivot, okay. How many pivots did we do? 1, 2, 3, which is the same as our number of rows and columns. So N pivots. So that's 1 pivot, that's 2 pivot, that's 3. And then our number of additions or subtractions is also 3 across columns. So that means our addition and subtraction, actually we can just combine it here, and rows. So our rows, we also did N additions or subtractions, right? Wait, no, I didn't. Yeah, the textbook wrote it differently. But okay, again, for each pivot, well, we did addition and subtraction down the N rows. So we did or perform addition, subtraction. Down N rows. Well, let's see if we did that. So here we did 1 row, here we did another row, and then here we did another row. So that makes 3, or that makes N in general, in order to get to this stage, to get this one. Okay, so in total, our operation count is actually, so I'm just gonna write total complexity. So this is something from the previous video, is O of N cubed, right? We did N pivots, so that's N. And then for each pivot, we did N additions and N subtractions, so that's another N times N. Then we did N rows, so that's another N, so that's N cubed. And so yeah, it's O of N cubed. And the back substitution algorithm can similarly be calculated for back substitution. Is O of N squared. How can I tell? Well, the one that we did before. We do this and then this. So how many multiplications did we do here? We did 3. And so we did N multiplications. And then how many additions? Well, it's N minus 1. We add these two, we get 2N minus 1. And then how many times did we do that same thing? 1, 2, 3. So we did it N times. So we did it N times 2N minus 1, which is just 2N cubed minus N. And so if we wrote it in big O notation, well, we get, wait, why did I say O(n) cubed? O(n) squared. N times N is N squared. So O(n) squared, because that's our dominant dominant term, yeah. So O(n) squared, which is our back substitution. Okay. Um, okay. So here we're actually a bit surprised, right? Because O of n cubed is actually pretty slow. So that's why we have to do something about it to make it more efficient, right? Because if you remember our previous video, well, we talked about computational complexity, where, let me just show a picture here. Do I have a graph for it? I hope I have a graph. There we go, right? O of n cubed. So here's the data, the input. Here's our time. So the more time, well, of course, it's slower, right? So ideally, the best is constant time, O of 1, big O of 1, followed by O log n, followed by O of n, O n squared, O n cubed, and so on and so forth. And so our Gaussian elimination took this much. O of n cubed, just pretty bad. And so we want to minimize, or we want to make it lower than O of n cubed. So ideally O of 1, but we could make it like O n squared, like our back substituting algorithm. O of n. O of n is also pretty good. O log n and O of 1 are really, really good. So yeah, it's this idea of making programs much faster. So let's quickly do that, right? And here we can actually make it slower. How? Well, we use one of the, I'm going to talk about another technique, and we actually call it the LU decomposition. Right? Yeah, that was my next one. So I'm done with Gaussian. Now I'm here in LU. So let's do that. So for LU decomposition, so yeah, again, each Gaussian elimination operation costs O n cube operations. And this can be computationally prohibitive for large matrices. So if we had bigger and bigger matrices, well, it's going to be extremely slow, right? So when working, okay, so let's do the same thing. So when we're working with the same matrix A, however, the operation count can easily be brought down to O n squared. So that's the idea of this LU decomposition or factorization, the same thing. So the purpose of this is, well, one of it, I think. So we say that our operation count can be brought down. So we can decrease our time down to O n squared, which is significantly slower compared to O n cubed. And so what does this do here? So we have our AX equals B, right? That's our linear system. And we want to split matrix A. So here the idea is we want to split matrix A into a lower triangular matrix. I'm pretty sure we talked about that. Did we talk about lower triangular and upper triangular? Or no? We didn't, did we? Oh yeah, we did. Tridiagonal matrix. We talked about it for a bit. Um, Actually, we didn't. Okay, let me just review it. So a lower triangular matrix. So that's L. And the upper triangular matrix. And so that's U. Now you know it's an LU. L for lower, U for upper. So we kind of decompose our matrix A into two matrices that are easier to compute. And so if we go back to our 3 by 3 matrix, well, the LU factorization scheme splits A as follows. So let's say, do another example here. For a 3x3 matrix, well, we say our matrix A is equal to LU. So let's actually show what that is. So A can be split into two matrices, and we multiply these lower and upper triangular matrices. I'm going to show it. So here's my matrix A, A11, A12, A13, A21, A31. So here's my 3x3 matrix A, 3, 2, 3, 3. Right? Let me just move. This is equal to our lower triangular matrix. So these are lower. 1, 1, 1. And then we have some values here. M21, M31, M32. Then these are zeros. So when it's a lower triangular matrix, we have values here. Right? Multiplied by my upper. So let's just use U. Could be any variables though. U12, U13, U21, or 22, I mean. U22, U23, and then U33. That's my upper triangular matrix. So what do you notice? Well, it's actually split by some diagonal, right? Okay, let's see how this works. Well, okay, let's do that. So so L matrix is lower triangular, U matrix is upper triangular. This then gives, let me just write this. So this gives, right, AX equals B, which can be rewritten as LUX equals B. This makes sense, right? I'm just replacing A with LU. As simple as that. And here you can see it's a, okay, let's draw this. Actually, this is a lower, this is an upper triangular matrix. How do I know? Well, there's the lower part. The lower part has values. So if the lower part has values, that's a lower triangular matrix. And these are zeros. And same goes for upper. So if it's the upper, now it's the upper set of values. It's the upper set of the matrix that has values, while its lower part doesn't, meaning it's zero. I hope that makes sense. Okay. And now from here, we can actually let y be equal to ux. So we find a coupled system. I'll explain this in a bit. So now, right, my A is LU. I have that. Now I assign variables. So now my ux is my y. And so what does that mean? Well, now I have two systems. So I have ly equals b, right? Because I replaced y with the ux. That makes sense. And yeah, my ux equals y. Now, why is this easier? Or why is this more efficient? Well, if you notice, right? Okay, let's go through the process of knowing why this is more efficient. But the idea is this is more efficient than just solving it directly using Gaussian elimination, right? So this is more efficient than Gaussian. Let's actually go through the process of why. So let's slow this. So the system Ly equals B. So now we have our lower. I actually can't quite visualize my lower and my upper. Oops. My lower and my upper. My y is u times a vector, u and x. Okay. Um, let's see. Okay, let's actually do it in matrix form first, and then we make the solutions. The textbook went ahead and made the solutions. So my L, again, is a lower triangular matrix. So I have 1, M2, 1, M3, 1. I'm just copying this. 1, 1, 1, M2, 1, M3, 1, M3, 2, 0, 0, 0. That's my L. My Y, here I made a new one. So let's say Y1, Y2, Y3. So Y is a 3 by 1 vector. And so my B has the following. Well, my B has the same thing as the, yeah, my B1 is just a result vector that has values. B1, B2, B3, right? Here I'm making it general. I'm not putting any numbers. And here we can actually just solve for the system. So, well, we can use, wait, here we use a forward substitute. Now we just solved it regularly, actually. Let's just do that. So we do this, and then we get this. And then the same thing. This, this. No, not that one. I'm wrong. This, and then this. Then for the next equation, this. Okay, let's do the first one. So the first one was this. So all I'm saying is 1 times y1 plus 0 times y2, right? Because here we're getting dot product. Plus 0 times y3 is equal to b1. And we can simplify. So we get y1 equals b1. That's our first equation. So y1 is b1. And then same idea, right? We do this, and then we get this. And then same idea. So if I just do it for all, well, I got m21, and I multiply that to y1 plus my y2, and then I should get a b2. And then for the last one, m31 y1 plus m32 y2 plus y3 is equal to b3. So I have these three linear equations. So that's a linear system. And surprisingly, this can be solved by O(n) squared, right? So this thing can be solved by O of n squared, forward substitution. So there's actually a name for what we just did, right? We started here, then here, then here, and then here, then here, then here, then here, then here, then here. That's forward substitution. The other one we did was backward. So um, we did here, then here, then here. here, then here, then here, here, then here, then here. That's backward. And apparently, whether you do a back substitution or a forward substitution, the complexity is the same. They're both O(n) squared, which makes sense, right? Because you're doing literally the same thing. One's just forward while the other one's backward. So that's a forward substitution, right? Okay, and then we do the same thing for the system ux equals y. And here, well, I'm not going to go through the nitty-gritty anymore, but basically we'll get these solutions. So we get u11 x1 plus u12 x2 plus u13 x3. This will give us some b value. Oh, no, some y value. y1, right? Actually, we can just draw this out. Yeah, let's actually do that. I want it clean, just so that I know what I'm doing. So my U is a matrix. So is the upper matrix, which is this guy over here. I'll just write that U11, U12, U13, U22, U23, U33, 0, 0, 0. That's my U. My X is a vector. So it has X1, X2, X3. My Y is again a vector, Y1, Y2, Y3. And then here we do a back substitution. So we do this, then this, which will give us this. Then we do this and this, which will give us this. We do this, then this, which will give us this. Okay, so let's write out the system. Yeah, so we have, oh, funny enough, I actually started from the upper part. Yeah. So I started from the upper part. I think I could do the same thing. I could start from the lower part. And I'd still get the same thing. But anyways, okay, let's just do it. U22 x2 plus U23 x3. This will give us y2, right? Then lastly, we have U33 x3, which will give us y3. And yeah, this can be solved. By this complexity, O(n) squared back substitution. So yeah, whether we do forward or backward, somehow it's the same, which is funny. And once the factorization is complete, well, the LU results in an O(n) squared scheme for arriving at the solution. So here we did 2 O(n) squared, right? So the total complexity we did was 2n squared, which is basically just n squared, which is way faster than doing it directly with Gaussian elimination. And so the note is, or the idea is, you should always use LU decomposition if possible. Otherwise, you're doing far more work than necessary in achieving a solution, right? So let's say total complexity is O of 2n squared, which really, we don't really care about the 2. So we just say O(n) squared. So it's faster, right? Here it's O(n) squared for one of my systems here. My other system is also O(n) squared. and then we combine those two operation counts or total or those complexities, and we get approximately O(n) squared, which is faster than O(n) cubed. So if possible, we use LU. Okay, so let's do an example of my LU decomposition algorithm. So here we consider a 3x3 matrix. Okay, now this is a practical example. And in this 3x3 matrix, let's denote it as A. 4, 3, 1, -2. Okay, I'm just copying the numbers. -4 and 5, 1, 2, and 6. And the factorization starts from the matrix multiplication of matrix A and its identity matrix. Right? So here, a lot of writing. Factorization starts when starts with A multiplied to identity matrix, which we'll call I. Let's write that out. So we have A is I times A. So my identity matrix is from a previous video. It's just that. And I multiply that with, well, my A matrix. And the factorization begins with the pivot element. So the pivot element is 4 in this case, or the first row. And to use Gaussian elimination, we would multiply the pivot by -1/2 to eliminate the first column element in the second row. And similarly, we would multiply the pivot by 1/4 to eliminate the first column element in the third row. These multiplicative factors are now part of the first matrix above. So let's actually see what in the world did we do. We multiply by -1/2. To eliminate the first column element, the first column element in the second row, -1/2. First, what does that mean? Like I'm trying to read it. I'm like, what? What? First, oh, okay, let me see. So here we're actually using Gaussian elimination. Okay, this is really confusing. So again, when we're using Gaussian elimination, we can either multiply any row by some constant, switch any two rows, or add. So multiply, switch, or add. Okay, so the first thing that the textbook did was multiply the pivot by what? -1/2 to eliminate the first column element first column element. So what's the first column? We're looking here in the second row. So we're multiplying to eliminate this thing, -2. And so this would give us, well, A is now, well, this is still 1, 0, 0. But here in our next one, now it's -1/2. Which is funny. Okay. Wait, let me see exactly what in the world happened here. Because I'm also confused. I can't see how it connects. Yeah, sometimes the textbook makes it really, really confusing to follow. Yeah, okay. Applying rule, eliminate entries. Top left. You want to eliminate the -2 and 1 below it. So to eliminate -2, we add 1/2 times row 1 to row 2. Wait, what? Oh, yeah, so the idea is we want to eliminate these two. So how do we do that? Uh, we can add 1/2 times row 1. So that's 2, right? Because row 1 is this guy. And then we put those values in row 2. Oh, okay. So that's why it was so confusing. I couldn't follow the steps. Yeah. So basically, yeah, let's not write this. Let's do uh pivot is 4, top left. Uh Eliminate -2 and 1 below. Oh, now I see why they underline. Yeah, because the idea is you want to make it an upper triangular matrix like this, where there's basically zeros here. So 2 zeros in the first column and 1 0 in the second column. So you want to make it like that using Gaussian elimination, which is what we did actually. Okay, so let's do that. And so here what we did was we add 1/2 times row 1 to row 2, right? So here we divided everything by 2, and then we put all of that to row 2. Or wait, no. Did we do that? Or yeah, times row 1, we put to row 2. And so yeah, uh, oh, that's interesting. Yeah, okay. I still find this confusing to follow. Um, okay. I'm not gonna dive into the steps. 1/4. But that's the idea. We want to make everything 0 here. So here our goal is to eliminate those two guys, or these ones. And so we were able to do that here, or at least the textbook did. 4.5, now 0, 1.25, 6.25. Okay. So what he did was he multiplied 1/2 to row 1, and he added that to row 2. Let's try. This is gonna be divided by 2, 3 halves. So that's 1.5, I believe. No, 3 divided by 2 is, yeah, 1.5. Let's do it decimals. 1/2 is 0.5. And then from there, what did he do? Well, now he said, okay, we multiply 1/4 to eliminate the first column element. Oh, and then what he did was he put that here. And then he multiplied 1/4 uh, of the pivot. So he multiplied 1/4 here. And then once he did that, he put that in the third row. Oh. Okay, wait. Let's actually try that. So 1/2 times row 1 is this guy over here. And then we put that to row 2. So let's quickly do that. So this is now 2, 1.5, 0.5. So those are the changes that happened, right? Here it's still the same. 1, 2, 6. Actually, let's make it red to see what changed. Then here we also do the same thing here, obviously. So we multiply 1/2, or well, yeah, we multiply 1/2 here. Um, okay. And then we get, this is still 0, 0, 1. So when we multiply 1/2, well, here we get 1/2. Still a 0 and 0. So we get this. Okay. But yeah, the idea is to make this zeros. My zeros are ugly. Zeros. Okay. Next. After doing that, well, now we want to eliminate the 1. So here we subtract 1/4 times row 1 to row 2. God, this is tricky. Okay, so here we have row 1, which we multiply by 1/4. So here we got 1/4, 0, 0, right? And then we put that to row 2. Oh no, to row 3, I mean. My bad. Row 3. So this should give me, okay. Um, oh crap, oh, I was supposed to switch. Um, hold, wait, okay. Wait, wait, wait. Uh, oh, so confused. Wait. Hmm. Yeah, because I didn't make the zero. Wait, let me restart. But oh, what draw that line for? Okay, let me. But that's the goal to make those zeros, right? So how do we do that? Well, okay. So how is this gonna look like? So for row two, oh, okay. So we want to multiply 1/2 to row one, and then add that to row two, right? So here's my first step. So my row two will now be row two plus 1/2 of row one. So 1/2 of row one, well, this is just two. This is, I don't know what that is. 3 divided by 2 is 1.5, I think. Okay, 1.5, and this is 0.5. And I want to add that to row two. So I'm basically updating what I have here, right? Uh, but yeah, wait, let me see. And here I do the same thing, so I get the half. So this is 1/2. This is 0. This is 0. I put that, or well, I add row 2. So 1/2 plus 0, still 1/2. This is 1, right? Because here I now add my row 2. This is still 0. So let's quickly do that. 1, 0, 0. Here's where the thing changed. So 1/2, 0. No, not 0. 1, 0. Go back to my black color. Done. That's my identity matrix. Now I do this. So this one hasn't changed. 4, 3, 1. This is the one that changes. So 2 minus 2 is 0. 1.5 minus 4, which is negative 2.5. And then 0.5 plus 5. Is that 5? Yeah. 0.5 plus 5. So it's 5.5, right? And this is still the same 1, 2, 6. Then the next thing I'm gonna do is to make my 1, 0. How do I do that? Well, to make my 1, 0, here in my row 3, well, I need to say, okay, my row 3 is going to be row 3, I subtract it to 1/4 of my row 1. So let's quickly do that. So if I get 1/4, well, this will turn into what? 1, 3 over 4? What is that? 0.75. And then this is 1/4, so 0.25. And then, so my row 3 minus this, right? So 1 minus 1, this becomes a 0. So that's good. 2 minus 0.75. Well, this becomes 1.25. And then 6 minus 0.25. Well, this becomes 5.75. Great. Goodness me. I actually should have done it in the first one too. But oh well. Let's do it after. 1/2, 1, 0, and then some numbers there. So here 4, 3, 1, 0, negative 2.5, 5.5. Can't see. And then lastly, the one that changed. So 0, 1.25, and then 5.75. Done. Okay, now we do the same thing here. So we have 1/4 of my row 1. So I have 1/4, 0, 0. I subtract row 3 from it. So 0 minus 1/4. Well, I get negative 1/4. 0 minus 0, I get 0. 1 minus 0, I get 1. So here I have, there's my change. Negative 1/4, 0, 1. Okay, and now what do I do next? Well, now I need to do more stuff so that I can factor out the others, right? So I'm going to continue factorization in my next pivot. So my next pivot is actually here, right? So I continue factoring. So let's see. How do I turn this to 0, right? As I'm thinking about it, not really sure. Um, okay, let me see. Hmm. So here we can actually add, or we can multiply 0.5 to row. So here we're saying row 3, right? I'm going to be multiplying 1/2 to my row 2. So let's see what that looks like. So if I multiply 1/2 to my row 2, so here I get, here I'm just looking at this. I get 1/4, I get 1/2, I get 0. Done. And I put that to row 3, right? So I have 1, 0, 0, 1, 1/2, 1, 0, and then my change, which is in row 3. So I changed it to 1/4, 1/2, 0. Okay, cool. Now I do the next one. And here, my row 2 of my other matrix. So I multiply 1/2, well, I get 0. I multiply 1/2, so 2.5. I divide that by 2, I get 1.5. Oh, I actually add row 3, my bad. Yeah, I have to add row 3. So plus row 3. So let me actually redo it. Wait, so this is 1/2, I 1/4, and then 1/2, and then 0. Then I added to my row 3 right now. So 1/4 minus 1/4, this is a 0, right? This is 0. And then 1/2 minus 0, or 1/2 plus 0 is just 1/2. So I treat it the same way. And then 0 plus 1, which is still a 1, right? So we're gonna quickly do that. Okay, I'm getting some practice with Gaussian. Uh, okay, and then last part. Um, So I multiply this by 1/2 and I add it to row 3. So this is still a 0 plus 0. I multiply this. Well, it's negative 1.25. I add it to here, I get 0. And then I'm pretty much done here, but 5.5 divided by 2, I got 2.75. I add it to here, 5.75. I got 8.5 actually. And here I get 4. I get 4. I get 3. I get 1. 0, negative 2.5, 5.5. And then what I changed here. So I get 0, 0, 8.5. And I'm done. I have everything. Right? Oh crap. There's actually, I probably messed up one of them. Anyways, but yeah, now that's the idea. Yeah, I think I messed up somewhere. Anyways, we'll see. Oh, so it's a 4.5. It's not, yeah, I messed this up here somewhere. It's supposed to be a 4.5. 4, 4. Okay, now we have that. And so my L is this thing here. Did I get it all? Okay, no, I didn't, surprisingly. Um, Let me see. Okay. I mean, it's my first time doing this, so. Hmm. Okay, my L is supposed to be 1/4 and negative 1/2. Okay, let me just, yeah, I'm just gonna say computation error or something. But it's supposed to be this. Otherwise, it's correct. Is that it? Yeah, that's it. And so from there, well, it's easy to verify by direct multiplication that indeed A is LU. Just like Gaussian elimination, the cost of factorization is O and Q. However, once L and U are known, well, finding the solution is an O of n squared operation. Okay, I'm gonna add a video there because it's gonna be a bit too long. But the next thing we're gonna talk about is still these ideas about linear systems. I'm gonna give a teaser actually. Give a teaser. So the next thing we're gonna be talking about is actually the permutation matrix. Permutation matrix. And basically, well, it's another way of making, uh, as will often happen with Gaussian elimination, following the above algorithm will at times result in a zero pivot. This is easily handled in Gaussian elimination by shifting rows in order to find a non-zero pivot. However, in LU decomposition, we must keep track of this row shift since it will affect the right-hand side vector B. And so we can keep track of the row shifts with a row permutation matrix. So yeah, this is the next thing that we'll talk about. So yeah, I hope you guys stay tuned and I'll see you all in the next one.